Okay, now, the College Board has asked my students 2 separate years to label these separate parts, and has asked a number of questions about what goes wrong and how this thing or that thing works, which all relate to this reaction. I know some of you have already seen this because you took AP Chemistry, raise your hand. Or regular chemistry, raise your hand. How many of you saw this in regular chemistry? I hope you'll forgive me. Some of my students did not take chemistry. Some of them had bad experiences there. Or terrible, apparently, experiences. It says either, but don't worry about it, because I'll talk about it. Now, children's, we only stamp the one that's early, not the one that's late. So I'm not giving you credit for the other one early, but I can't give you credit for this one late.
What if this one was on time, but you just stamped the wrong one that day?
Then you gotta catch it that day, because it becomes your fault when you gotta stamp it that day. Watch this. We're gonna probably stop around here today. If I can get through this, we're good enough. Tomorrow we can do this part. It's actually mellower than it looks. But in order to talk about this, I'd like to do a little nuclear physics for dummies band-aid over here. Okay, here it goes. Please look up. And I'm assuming that even if you copied this, you'll be writing other stuff because I say things that aren't written on the board. First, probably the 7th or 8th grade, you learned a very simplified concept of an atom that had neutrons and protons in a nucleus with electrons spinning around in rings. Raise your hand if you learned that in 7th or 8th grade. Something that I learned wrong is that neutrons and protons are an equal number. Something else I learned wrong is that those electrons are in rings. You need help somewhere? Oh. Always happens, every day. I hate that thing. Okay. Those electrons are in rings. No, they're in clouds. The neutron and proton numbers are not necessarily equal. As a matter of fact, more often than not, they're unequal. We don't have to know much about electrons because this is nuclear physics, which is what happens inside the nucleus. So for the electrons, they have a negative charge. They don't weigh very much, and that's about all we're going to say about them. You may remember from earlier in your education that extra electrons makes a negative ion and missing electrons leaves a positive ion. That doesn't matter. Today we're not going to do anything with electrons for the rest of this unit. We do need to talk about the protons and the neutrons. I'm assuming that you have these notes on your paper. Protons have a positive charge. Everybody must know that they have a weight of 1 atomic mass unit. That says AMU. If you didn't know, that stands for atomic mass unit, which is a really, really, really small measurement of mass. It's very, very, very lightweight. But protons do have a known weight. And the key fact that you must know is that the number of protons decides which element. You can see that the atomic number is the number of protons. Everybody has to know that. And elements are just a name we give to the number of protons. So Anything with 24 protons is called chromium, and anything with 74 protons is called tungsten. That blue number is fixed. It's always going to be tungsten if it has 74 protons. Elements are just the names we give to proton numbers. Is there any doubt that thing's going to randomly decide to go back home? No doubt. Now, when we start to talk about neutrons, things get a little bit fuzzy, and I have to warn you that things are gonna get a little bit fuzzy now. I mentioned them earlier. Inside the nucleus, along with the protons, are neutrons. Those have no charge. Gotta know that. They weigh 1 atomic mass unit. Gotta know that. And the number of neutrons is actually kind of arbitrary and hard to explain. Things are about to get a little fuzzier. I always tell my students that the protons and neutrons are held together by something like gravity. And we got to be really clear. I don't know if you want to put this in your notes or not, but I really need your attention. When I say gravity with these things on it, I should be really clear that inside of the neutron there are a tremendous and complex and unknowable number of forces, attractive and repulsive, between those little parts. You could pretty much start your grad school career now and spend, I don't know, 10, 20 years and still be learning new stuff and writing new stuff about the forces inside of that nucleus. There are magnetic forces, repulsive and attractive. There is something like gravity, which is matter just clustering together. There's kinetic energies. There's a whole bunch of crap that's totally over my head and above my pay rate, and I apologize that I can't help you with that. So this is the part where, like, I don't know, we're all just going to agree to limit our understanding for the sake of this conversation. We can pretend, just for now, so that we can be friends and continue talking, that those protons and neutrons are held in that nucleus by a complicated combination of forces. Now we're just going to call something like gravity that holds them all together in a cluster. Anybody want to add something, because you've had classes with better chemistry teachers than I am, about those forces? Is there any problem? Am I stabbing anybody in the back by calling them quote-unquote gravity? Gavin goes, okay, thanks. Here we go. That number can be flexible. You could theoretically possibly have a lot of different numbers of neutrons for each set of protons. But the sum of those forces gives you an average number, and any atom with less neutrons makes what we call a light isotope, and any atom with extra neutrons makes what we call a heavy isotope. So for uranium, the average is 238. Anything less than that would be called the light isotopes, and anything more than 238 would be the heavy ones. 238 being the weight of all those little pieces combined. The mass of all those little pieces combined. This is the part where I'm hoping everybody's awake and will please ask me questions, because it gets more confusing later, and I want to make sure that I've kind of not made mistakes for you. Period 3 is critically quiet, and I just don't know if I've done you wrong. Okay, winging it. Can you bring up the calculator on your device, please? Children, watch this. Watch this. If the atomic mass on average of uranium is 238, and there are 92 protons, 238 minus 92 is 146 neutrons. I'd like everybody to notice something, please. Uranium, on average, has 92 protons, because we know that that's what we call uranium. And how many neutrons? 146. Do you notice how many bonus neutrons that is above matching? That's like 54 extra neutrons. Just random baggage. Enough to match the protons, plus 52 others just sort of thrown in there. I want everybody to remember those extra neutrons, please. They're going to come back to be a problem later. I'd like everyone to know that the average uranium has 92 protons like every uranium, and then on average 146 neutrons, which is a whole bunch of neutrons. Random baggage. Uranium is a metal. Uranium is mined as ore. It's stuck to rocks. Like most metals, you find it as like streaks of that metal in rock. You can grind it up into powder, heat it up very hot, the metal gets runny and pours out of the rocks. You throw away the rocks and you collect all that molten uranium and you make a big blob of solid uranium metal. If you could grind up that uranium and weigh every uranium atom, every single atom, you would find this. Please look up. You have to know this number. About 99.3% of all those uranium atoms would be that average weight, 238. You have to know this, that 99.28 are the average 238 uranium. But in natural uranium, about 0.72, less than 1%, a teeny amount of those atoms are a light isotope, uranium-235. This matters. You'll see why. We're about to talk about that for a bit more. Yeah.
But if the mass on average is higher than 238, isn't there some that's above 238? Like it wouldn't be.
Those are the electrons added in.
Really?
Yeah. So the 92 electrons adds up to almost 1 atomic mass unit, doesn't it?
I don't know. I just thought they weighed like nothing. But
I think they weigh 3 zeros and a 1, or 2 zeros and a 1.
Okay.
You should Google this. I don't know, bro. I'm willing to be challenged. Basically, I've kind of self-educated myself. I did really well in chemistry through college, but I didn't learn this there. Or if I did, I don't remember it. So this is information I took off the interwebs.
Okay.
Please educate me. I know what you mean, that the number is higher than 238, so the average should be higher, right? I think if you add together the 146 plus the 92, you get 238 even. And then if you add together the 92 electrons on average, then you get like a 0.02 or something. Maybe 0.02 here? Or maybe there's some 239 here that I just got. Yeah.
Percentage-wise, did you just subtract from 100 for that? Because there's the other isotopes too that would
I was under the impression that the other isotopes are exceedingly rare, way down around 0% in frequency. I know that 236 does not exist in nature, it's inherently unstable. That 237 is exceedingly rare, so there's probably a lot of zeros and a 1 for the 237. And Gavin points out that since the average is above 238, we might have some 239s in there. I thought that the average was above 238 because of the electrons, atomic mass included. Okay. Now for everybody else. This, please look up, plain old uranium metal is a really crappy plain old metal. You might be surprised to know that it's very common all over the world. We have it in Carpinteria and Summerlin in our bedrock. It makes its way into the United States as really cheap cast iron pans. Uranium is just like a really relatively common, very, very dense and heavy metal. We in the United States use a lot of uranium to make really, really dense bomb tips so that they will break rocks when you drop them out of an airplane. They're called bunker busters, and they're a class of really dense, heavy bombs that when you drop it out of a plane will like travel through the air, and when it hits people that are underground in a cave get collapsed underneath it. You bust bunkers with dense metal. Uranium is really common. Yeah.
So it's not like glowing green?
No, it's not really. You could have it at home and you wouldn't know. Average uranium is frankly just not a big whoop, because 99.28 is that average stuff that's not of any particular notability. It's just riffraff. Yeah.
You're right.
No kidding.
Yeah, it doesn't go above.
I am never right. Wow.
Right.
Okay. So that's just the electrons?
Yeah, because it said the isotope mass of 238 is like 238.05, so it makes sense. That's the electrons.
Wow, I was kind of nervous because I was really just winging it. All right, watch this. What, bro? You think you can do this? It's so scary for me. I don't know anything. All this is above my pay rate. I don't have any idea what I'm talking about all day long. Is this so scary? I got kids that are like 100 times smarter than me that ask me really good questions, and I'm like, yeah, I'm totally good for this. Here. That regular old uranium that you find in the ground, might as well use it to make crappy pots and pans because it's not useful for fuel. Please look up. To make it fuel grade, you have to do something called enrichment. That's a vocabulary term. Where you need 3% of uranium to be the light isotope. I gotta take a side trip and then we'll come back, okay? So side trip. Let's pretend that my class has 1% geniuses. 1%. Out of 100 kids, one of them is a genius. And I want to have a higher percentage of geniuses. I've got two choices, right? One of them is I could recruit more geniuses somehow. And if that fails, how could I raise my percentage geniuses? Get rid of the other kids. Does that make sense to everybody? There's two ways for me to have a class with a higher percentage of geniuses, right? Add more or subtract the ones I don't want, right? Now. What?
Or teach them.
You don't get to make geniuses. Okay, watch this. That 0.72 is not enough to make nuclear energy. It just so happens that 0.72 is a really low percentage of the useful stuff. I want to get rid of this stuff so that it comes up as high as 3%. So if I start out with this much uranium, I got to dump a bunch of the crappy stuff so that the remainder is 3% of the target. Here's how we do that. Take the rock, grind it up into powder, suspend it in fluid, stir it up, squirt that into a whole bunch of centrifuge tubes, and spin it really, 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 really fast. Because when you spin it really, really, really fast, the denser stuff goes to the bottom of the tube. Then you take that plug out of the tube, you shave off the densest at the bottom, grind it up, do it again, spin it, take it out of the tube, shave off the most dense, grind up the remainder, make it into a powder, put it into the solution, squirt it into the centrifuge, just spin it around. The densest keeps going down, so by removing the denser uranium-238, you've enriched the remainder to be a higher percentage of 235. Anybody want to ask me about that? They better not do that, because the UN will sanction you. You may have heard that Iran got in trouble for enriching uranium. Many people are concerned that if you can go up to 3% 235, you can keep going. All the way up to 90%, which is weapons grade uranium. And that would allow you to build a nuclear bomb. And we don't want anybody else to have those, just us. Please look up. This is called fuel grade enrichment. You have to do that to build a nuclear power plant. If you keep doing that same thing, where you grind it up in centrifuge and grind it up in centrifuge, you get up to 90% enrichment, which is weapons grade. You can build a bomb with that. But we're not building bombs here. Bombs are a different technology, so we don't talk about bombs here. Plus, they're inherently evil. We're just going to talk about making electricity here. Okay. We got our enrichment, we got our atomic number and averages and symbols and stuff, we got our nuclear physics for dummies. Ask me anything you want, or I'm going to start number 36. We're good? Going for it? Go for it. You take a whole bunch of that enriched uranium and you shape it into little pellets and you stack them inside of little tubes, and those are called fuel rods. My dad has a pen holder on his desk that's a fuel rod assembly. And it's like a little ring with all the little cutouts and all the little tubes in it that you refill with uranium pellets. It's pretty cool. You can use it for pens. Inside that fuel, watch this. You use a really fancy slingshot to shoot neutrons at the 235. And I'll come back to why, but please look up. When 235 plus a neutron makes 236, that is inherently unstable. It cannot hold together, and that's going to go, and it'll split. That atom is going to break up. That's called fission, splitting the atom. George is texting people about it because it's such a big deal. And we're going to talk about what happens when you split an atom, but first I got to talk about why it's unstable. But first I got to check to see if everybody got that. 235 plus 1 neutron makes 236, and that doesn't work. That splits. You can't have 236. Look over here, please. Remember when I told you that we're going to use gravity to be a sloppy, fuzzy term for the sum of all the forces inside of a nucleus? If you actually sit there and you diagram in 3 dimensions all the protons and all the neutrons inside this atom, you can't get the arrows to balance. You can't balance all of those forces. When there's an extra neutron, It sort of pulls this way, it pulls that way, and it pulls this way, and it pulls that way, and the whole thing destabilizes and it falls apart. 236, because of that complicated web of forces that I'm not qualified to explain to you, because I don't know what the hell that is, for some reason that's over my pay rate, 236 really does not hold together. It falls apart. It cannot exist. You can make it for a split second and it goes, falls apart. Inherently unstable. Now, when that splits, you could get a gazillion different products, but the most common are, you have to know this too, I'm sorry, molybdenum 103 and tin 131. Molybdenum, M-O-L M-O-L-Y-B-D-E-N-U-M. M-O-L-Y, like Molly, B-D-E-N-U-M. Molybdenum. Tin, S-M. And you can probably all spell tin. I gotta take another little side trip really quick. When I came to the United States, I was totally fresh off the boat, like 8 years old, and like just barely been here, like a few days. And in Argentina, we drank a lot of Tang, which is like a powdered fruit juice made from tangerines. Anyway, when I came to the United States, we couldn't get Tang, but my mom and dad went to the supermarket, and they're like, "Look, son, we found you this stuff called Kool-Aid. The Americans drink it." And I was like, "Kool-Aid? That's weird. It looks horrible." And I didn't like Kool-Aid, but on the back of the Kool-Aid packet, there was like a contest where you could like put your name on it and mail it to the Kool-Aid guys, and they would give you a $100 gift certificate for Toys R Us, and I won. I had been in the US for like 47 days or something, and I got an envelope from Kool-Aid guy, and I opened it, and it was a $100 gift certificate to Toys R Us, and I was like, this is the greatest country on earth.
American.
I was like, so America, like, holy crap, I just got here. I get beat up at school every day, I don't know anybody, and somehow this country just gave me $100 at Toys R Us. In 1985, $100 at Toys R Us was like $10 million. To like a poor immigrant, $100, like holy crap.
What'd you get with it?
So many Legos.
Good choice.
They had just come out with like the castle series, so I got like 2 big castles, like the big boxes, and like a couple little ones, like the archers. I spent like $101.14 because I took all my change and like got it to balance out like to the penny, all the money I had. I was so happy. My mom and dad were struggling, you know. Immigrant experience isn't always easy. And my mom and dad were like super fighting, and I think their life was really hard for a while there. I'm sure that their life was really hard for a while there. And me, I was just locked up in my room building Legos, like so stoked every day. I was so pumped. I still have a little brother. He's younger than me by like 4 years. And so on my nightstand, which was like a really low table, I had my Lego castles, and then my punk little brother, who was like 3 or 4 or whatever, like he knocked him over. And so I built this castle. It was about that big, and it had like 4 towers and like big sturdy walls that had like pathways on the inside where little Lego men could move around, and like it had like a thing on the top where all the archers could move and you could set them up to like shoot down. It had a drawbridge in the front. Oh, that was badass. I was super into it.
It was like, it's dark gray, right?
Kelly?
It was dark gray.
Light gray. Yeah, and dark. It was like a mix of grays, yeah. So it had a stone pattern.
Yeah.
The little quarter pieces were light and dark, cobbled. Yeah. When that thing fell, it broke in the middle into 2 pieces. And I got in a fight with my little brother. My parents reminded me to be kind because he's a little dude, and I got over it. And I rebuilt my thing, and I put it back up there. And like the next day, he knocked it off because he was just interested in what I was interested in because he was a little boy, you know. And so the thing breaks, and I'm like, oh, I hate you, Juan, you're the worst brother. And I go to rebuild it, and I'm like, huh, that broke in the same place as yesterday. So I put it back together, put it on the table, started to walk away, and like, young scientist, I'm like, broke in the same place, huh? That's why I pushed it off again. And I went, ah ha ha! Complex structures have inherent weaknesses.
Oh. 8 years.
And so I put it back together, and I put it on my stupid nightstand, and I pushed it off again. And I was like, huh. And you know, the little bridge over the drawbridge, like where the walkway went over the drawbridge, like sometimes it would break on this side, and sometimes it would break on that side, and sometimes it would break in both pieces, but that little thing was the weakness. And pretty much the left wall and the right wall, they never broke. On the back, sometimes it would break like just on the top, and sometimes little pieces would fall off, but that's a really important metaphor now. Because this structure, on average, when it breaks, has some variable number of chump change, little neutrons left over. And really, you can get all sorts of decay products, but these are the most common. You'll notice that they are the average decay products. And here's something that we have to explain. These are very, very heavy. Molybdenum usually weighs 96 atomic mass units. But that one weighs 103. That's a lot of extra neutrons. Check this out. Tin usually weighs 119. But this one weighs 131. That's a lot of extra junk. Look at this. Beryllium has 4 protons and 5 neutrons, only 1 extra. Carbon has 6 of each, no extra neutrons. As you get bigger, there's more and more miscellaneous crap. Like nickel has 28 protons and 31 neutrons, a couple extra. You understand what I'm saying? There's like the equal number and then a couple extra. Watch. Zirconium has 40 protons but 51 neutrons. That's 11 extra. As you get bigger, they've got more and more junk. Just like a bigger car has more and more miscellaneous crap. When I had a little moped, I had a bungee cord that I didn't always use. Sometimes I had a dish towel so I could dry my helmet and my seat. But my Tacoma, I've got like 500 pounds of junk in there. I got tools. I got an old wetsuit. Right now I have a bunch of wood from a project I haven't finished. I got my climbing gear in there. I found a burrito in my car a few years ago that I'd forgotten like 3 years earlier underneath one of my seats. My homie Jesse and I went climbing in Las Vegas and we bought extra burritos, and then on the road somehow one of them got kicked underneath the seat and we just forgot about it. A car like mine could hold a lot of junk, and if one of you has a really, really, really big car and it's been around for a long time, it's probably full of miscellaneous junk, right? So, please look up. The bigger elements can hold a bunch of junk. Remember, we just did the math. How many? 146 neutrons for 92 protons in uranium. That's a lot of, but you know, it's a big element, so it can hold a bunch of junk. When that thing splits, all those extra neutrons, they gotta go somewhere. Now comes the part where you need to interpret this in your own writing, but get ready for this. The decay products have way more neutrons than normal. They are extremely heavy isotopes. That makes them, please look up, very, very unstable. I put 2 asterisks on there. Those are more radioactive than the reaction was. Can you imagine taking all the scrap junk out of my Tacoma and trying to distribute it over 2 mopeds? Those would be death traps. All that junk trying to ride the little moped? Likewise, a smaller element cannot manage all those extra neutrons. And those are going to fall off, just like junk on the freeway. Highly radioactive. I'm asking you to explain something that I just band-aided you in 20 minutes. It's tricky, but you have to be able to explain why the waste products of fission are the most radioactive thing. All of the bonus neutrons of a big atom have to go somewhere. And now they end up as a burden, unnaturally extra, on a much smaller atom. Question?
So the neutrons fall off the smaller atom, or no?
They will. That's what radioactivity is. It's atoms falling apart. It's just pieces falling off. Like when you see people driving down the freeway and stuff's not tied on right and it starts to fall off, that's dangerous and stuff. My wife almost got in a horrible car accident yesterday because she was driving behind somebody who didn't have stuff tied on their car. She told me about the accident, not about what it was. I don't know what it was tied on the car. I have to ask her. I'm a bad listener. You don't know I'm a bad listener, huh?
Yes.
Now, all of those forces, you know, that we're holding together that big old atom, when you split that into smaller atoms, you're going to have a bunch of leftover energy. So for one thing, you're going to get a lot of heat, the heat that we use to boil water to make the turbines spin to make electricity. Remember that this is just a fancy heat source. So we're going to talk about that heat management tomorrow. But there's one last thing to talk about. What's my time check? We got 7 minutes. Watch this. Those 2 neutrons, extra neutrons, might be 2, might be 3. Those are really dangerous. You see that exclamation point? Exclamation mark? You call it exclamation point or exclamation mark? Whoa. You can use both? I just noticed that. Okay. Those are really sketchy. That's a scary problem. Can anybody explain to me why extra neutrons are going to be a sketchy problem around there?
Yes, they can fission.
They what?
They can fission with uranium-235s again.
What uranium-235? I just took it and made it into 236.
But there's more. There's not just one uranium-235.
There's how much?
Reactor. There's a bunch.
Right, it's about 3% of all that uranium. And 238s don't absorb the neutrons, so they'll just travel through the fuel until they find another 235. Does that make sense to everybody? That this is not a single atom that we're playing with. I just zoomed in on one atom. But this is part of a fuel rod, which is part of a fuel assembly. A good way to think about this is if you have a room full of firecrackers and you light one. When that one goes pop, it's not a big deal. You can hold that in your hand actually. But those sparks, where are they going to land in a room full of firecrackers? On other nearby firecrackers. And what's that going to do?
Light them up.
Light all of those. And that's going to make a whole bunch of sparks that are going to land on all the positive feedback loop. Chain reaction. Anybody ever heard of the chain reaction thing? That's a chain reaction. Please look up. The product of one fission event includes the fuse or the spark to start many of them. Don't forget that the fuel is going to lose a bunch of neutrons also. All that extra baggage that they can't hold on to. So here's the really, really sketchy thing. When you destabilize one of them, you've now started this cascade of neutrons that'll keep destabilizing the rest. That's the scary part. That's the chain reaction. That's the disaster that we have to avert. Tomorrow we're going to find some way to manage those neutrons. Because if those neutrons keep going, this is crazy runaway reactions that'll melt everything. So much heat output that this whole thing would just collapse and melt into the ground. This is where I needed to get today. Who wants to ask me something? I always feel very nervous doing this. I realize that this is over my head.
You know when the next containment structure for Chernobyl is
I don't know if it's done or if they're just trying to figure out how to move it or if they're almost done and they already know how to move it. The unfortunate comedy is Belarus is pretty close to Russia and they call it Russian dolls. So there's already one containment, I think this is the second containment structure, and the third one's getting ready to cover it up.
It's on like
Take a picture of it before you turn it.
Did we already talk about this?
I don't know if it's a video or what's up. Well, like, by the fourth or fifth one, it's going to be the largest building in the world.
Right, and that reaches the end of engineering. They can't make things eternally big. And so you can only cover up so many containment structures with another containment structure. They don't last very long. Anybody else want to ask me anything? Derek, Chloe, will you turn off the...
It's blocked out.
Oh.